Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So, before I get started, I just want to remind you that today is the last lecture for this course. I'll be putting out the exam format as soon as possible. I'll also include a mock quiz, just like I did for the midterm. So just keep an eye out for this. But that being said, there's a scheduled time, and we're going to be doing our exam over your courses, as per usual. Anyways, let's get started. So last day, I started talking about this idea of a reduction. So I thought it would be valuable for me to do an example with you. Now, from a complexity theory standpoint, there's this idea of a reduction, but oftentimes I would like to have the reduction take a certain amount of time. And here's the as a chap might say, this is the big brain idea. So what I'm going to do is I'm going to consider so-called polynomial-time reductions. So that means that if I give you a reduction, it has to run in polynomial time, hence its name. I must stress that in the model of computation that we are studying, it's implicit that the resulting instance also is polynomial in the size of the original instance. So this is just because whenever we allocate space, that costs time in our model. Just be aware that that's it's an implicit assumption that we're making in our model. So, you might ask, okay, so how do I represent a polynomial time reduction? Very often, this is the symbols used. So I would have pi1 polynomially reduces to pi2. So it's a less than or equal to with a p beside it. So it says subscript beside it. So that's how I'll be representing the polynomial time reductions. Note that there's many different kinds of reductions. For example, the one I gave you the other day is a so-called mapping reduction. So anyways, the big brain idea here is that if I had a polynomial time algorithm for pi2, and I know that pi1 polynomially reduces the pi2, meaning there's a polynomial time reduction, if you think back to the picture I gave you last day, that means I have my big box. That means that I have a reduction that takes polynomial time, but I also have a polynomial time algorithm for pi2. That means that I can solve pi1 in polynomial time overall, because all of the time it takes is polynomial. And keep in mind, that's a very interesting thing that we're going to see plays an interesting role in some of the things we're going to talk about a little later. So I thought it would be important we do an example of one of these polynomial time reductions. So I'm going to introduce two different problems to you. These are both difficult problems. So just like I talked about the 0 and knapsack problem being difficult, this is another couple difficult problems. So I haven't really laid down what exactly that means, but here's the first one. We have the Hamiltonian cycle problem. Some people call this the Hamilton cycle problem. So given an undirected graph, so just have an undirected graph, we ask if G contains what we call a Hamiltonian cycle. What a Hamiltonian cycle is very simple. It is a simple cycle that contains every vertex in the graph. So the idea is that if I have my graph, it should be that I can find a cycle that visits every single one of the vertices, but doesn't repeat a vertex. So I want to know if that exists or doesn't exist. That's all it is. So I give you any undirected graph. I'm implying that it's a simple graph, by the way. Here's another problem. This is called, now you may have heard of this problem before. I'm going to introduce its decision version. This is called the traveling salesman problem. I'm going to denote it as TSP DEC, DEC. So this is the decision version of, or decision variant. I'll usually use that phrase to refer to an optimization problem's decision problem version. As I mentioned the other day, there's oftentimes, if I give you an optimization problem, there's a natural decision variant of it, where I can ask the same kind of question, just as in the form of, like I can take the problem, I can formulate it as a question. So here's an idea. So this is what the traveling salesman problem would be if I posed it as a question. Given a weighted complete undirected graph, so remember this means that every vertex is adjacent to every other vertex in the graph. It's undirected. I'm going to call this graph H. It's going to have N for its vertices, and F is going to be its edges. and I'm going to have an integer k. I'm going to ask, is there a simple cycle at h with every vertex in this graph? That, and I must stress that if I give you such a cycle, we call this a TSP tour. But I want to have it, I want to know if there is one such that if I add up the edge weights of all the edges in this graph, when I get my cycle, I add up the edge weights on the cycle. I want to know if this adds up to at most k. So there's another way of thinking about this problem. If you think about it, it kind of reminds you a little bit of something I said over here, right? So remember, it's a complete graph. So if I find any cycle that consists of all the vertices, what is that? What is that? So if I find a simple cycle that has every vertex in it, what is that? I'll give you a hint, it's right there, right? It's a Hamiltonian cycle. So notice that in the formulation of this, what I'm trying to do is I want to know if there exists a Hamiltonian cycle where if I add up the edge weights, that the edge weights, when I sum them up together, sum up to no more than k. So thinking about that intuitively might give you an idea that maybe there's actually a relationship between these two problems. So I must stress that I will do an example with both of these when we get to the reduction, okay? So I want to show you how I can formulate a polynomial time reduction so that I can take any instance of the Hamiltonian cycle problem and I can convert this into an instance of my traveling salesman problem. So I'm going to show you how I could do this. So remember, the reduction, the whole idea of the reduction is that it will take any one instance of the original problem that I have, so in this case, the Hamiltonian cycle problem, and I will build an instance of the other problem. So pi 1 in this case is going to be the Hamiltonian cycle problem. Pi 2 is the traveling salesman problem. So I must stress it's the decision variant, but for the sake of our discussion, I'll just keep it abridged and I'll just refer to this as the traveling salesman problem. So just be clear, usually people when they talk about the traveling salesman problem, they're normally talking about the optimization version of this, where you compute the least weight Hamiltonian cycle. So anyways, here's the idea for the reduction. So we'll actually carry out an example and see the connection between these two problems. So here's the idea. I'm going to give you a polynomial time reduction. There's that notation right there. And it's going to run in quadratic time in the number of vertices of the original graph. So I give you an instance of the Hamiltonian cycle problem. So I'm going to give you graph G, and I'm going to build you in polynomial time a weighted complete graph H as follows. So I'm going to assume that the edge set, so all the edges of H, is just going to be empty at first, then I'm going to algorithmically build H in the following way. So first, I'm going to assign its vertices to be the same vertices as in my original graph. Then I'm going to go through each pair of vertices in the original graph, G. So if there is an edge, UV, in the set of edges, then what I'm going to do is I'm going to add an edge to F that has weight 1. Otherwise, if there is no edge, UV, in the edge set for G, then I'm going to add an edge with weight 2, with those two endpoints. Then the final step is to assign K, that was the number that tells me the total cost of the TSP tour, could be at most. I want to assign that to be N. Now you might ask, why N? This all comes down to how we're going to draw the connection on these two problems. So remember, the core idea of the reduction is that I can convert or build instances from one problem and turn them into problem instances of the other problem. But there's another part of the reduction. Does anybody remember what's the other big piece of this? Can it be that when I build the instance over here, like for the ones for pi 2, can they have different answers? Like, can it be that my decision problem for pi 2, like, can it have a different answer? So think about it. So there's two big pieces for our reductions. We had it where we build the instance, but we're adding an additional constraint that it has to be done in polynomial time. But it also, for our reduction, we had to have some way to make it so that whatever we build, we could be able to efficiently test that it in fact has the same answer, right? So we have to know that it has the same answer as our original problem does. That's at least one classical view of a reduction. Obviously, you can make small wrinkles in this, but that's how I'm going to define it here for you. So here's one way you could view this. It manifests as a theorem. So you could actually prove this based on this construction, is that there is a Hamiltonian cycle in G, so that's our original problem instances graph. There's a Hamiltonian cycle if and only if H has a TSP tour with total length at most K. But what's K? It's N. So that means that when I talk about my graph G and my graph H, now remember, H comes from G. So this isn't just any old arbitrary H. This H is highly related to G. So we're talking, when I say H here, I'm talking about the one we build from this reduction. So there's a very beautiful property that exists between G and H, is that if I want to figure out if there's a Hamiltonian cycle, this theorem tells me I have a way of checking that. So the very simple check is that if it has a TSP tour of total length at most n, then it has a Hamiltonian cycle. So in essence, what I've just described to you is that if you could build this and you actually had an efficient algorithm for TSP, traffic salesman problem, then what you could do is you could effectively lay this theorem out and you could say, hey, look, is the optimal answer at most n? And if you could check yes or no, right? So if the answer is yes, then most certainly that means there's a Hamiltonian cycle. And this proof, if you actually look at the proof of this, which I'll have in the notes, which I'll give you an intuition for in a moment. If you have this, it gives you the recipe for building the Hamiltonian cycle. So effectively, this theorem gives you an ultimate detector for Hamiltonian cycles, assuming you had an efficient algorithm for the traveling salesman problem. Is that kind of wild? So that means that, so if you think of it like this, remember our idea of the reduction was that if I pi 1 reduces to pi 2, that means that pi 1 is at least as hard as pi 2. So it means that if I had an efficient algorithm for pi 2, then I could solve pi 1 also efficiently. But the whole idea is that by having a polynomial time algorithm now, for my reduction, I can guarantee the whole thing runs in polynomial time. So that's a very interesting bit of piece that we're going to need for all of our theory we're going to talk about today. So let me do an example of us applying this reduction. So I'm going to give you an intuition for both of these and why this theorem is true. But if you want the details of the proof, I just have them in the notes. So if you want to see the full proof, it's just in the notes. So let's do an example. So I'm going to take a graph G and I'm going to show you how you build H. So let's build one. So let's do an example of applying the reduction. So suppose that G looks like this. Suppose I have 4, 1, 2, 0, 3. And suppose I connect it up like this. Yeah, let's go with this. Let's go with this. So this is G. So this is my input graph for the Hamiltonian cycle problem. I have a question for you. Does there exist a Hamiltonian cycle in this graph? So if you have, so is it yes or no? Remember, it's a decision problem. It has to be one or the other. Is there a Hamiltonian cycle in this one? Okay, so let's take a look and see where we could find one. So here's a natural one for me to point out. Let's see. I think I spot one here. We could go 4, right? We could go from 4 to 1. Then I could go 1 to 2. Then I could go 2 to 0. I could go 0 to 3. And then I could go from 3 to 4, right? So there's my Hamiltonian cycle right there. So that means that this would be a yes instance. Very good, very good. So one thing I will note is that because I don't include, it's a simple cycle, so I only count vertices once. So this implicitly assumes that there won't be duplicate edges in this cycle. This is because every time I pick an endpoint, I have to pick it distinctly. That means that if I go over it again, that means I may have to repeat an edge, possibly. But I'm enforcing that the number, like the vertices are all distinct in the cycle. I'm not going to care about its edges. That's the short of it. There's actually another notion of a special kind of cycle like this. So notice I want a simple cycle so it doesn't repeat the vertices. There's another one called an Eulerian cycle. That's where you don't repeat edges. There actually do exist efficient algorithms for that problem. So if you want to compute an Eulerian cycle where you want to know, okay, does there exist a cycle that doesn't repeat edges more than once? There actually does exist an efficient algorithm for that one. It actually uses some of the techniques I've showed you in this course. So that being said, let's apply the reduction. Let's see what happens when I do that. So this is G, and let's build H. So I'm just going to first what I'm going to do is I'm just going to draw in the graph like I had it. So I'll start with the vertices because in step 1 I make the vertices the same as the ones I had in G. Now, remember in the construction, I go through all of the edges, right? I go through all of the edges, and if there is an edge that's in the original graph, so I go across all my pairs of endpoints, if there exists an edge in G, I'm going to include it, and its weight is going to be 1. So I'm going to have edge weight 1. This will 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 have edge weight 1. Edge weight 1. I think I got them all. 1, 2, 3, 4. I think I got them all. 1, 2, 3. Got the 1 there, 2 there. Yeah, I think we got them all. So now I have to add in edges for where there's no endpoints in the original for an edge. So let's do that now. I'm going to include them in blue just to illustrate that I'm adding in these edges as well. So now I'm going to add an edge weight of 2. So wherever I don't have an edge whose endpoints already consist of an edge in G, I'm just going to include it. Its weight is going to be 2. So I have 1 there, have 1 there, have 1 there. So some people call this, by the way, edge completion. If you're ever studying planar graphs, there's actually a construction that's called edge completion that uses a very similar construction to this. I won't have time to show you it in this course, but if I were studying things on planar graphs, use edge completion very often, and it involves turning a graph like this into this by imposing or adding an edge weight on wherever edges don't exist, usually to impose some geometric space that you want to lay everything down on. But here, I'm just going to make them 2, just to keep it simple. So anyways, I go through here. Okay, that needs a 2. This edge. We need this one, this one, this one. Let's see, this. There, I think I got them all. Right, I got my occult symbol here. You know I'm up to bad stuff when that happens. I'm mischievous, of course. I'm just joking around, of course. It's just a pretty star. So anyways, now I have that. And lastly, of course, I assign K to be, let's see, how many vertices do I got? 1, 2, 3, 4, 5. So I have K as 5. So now I have built my traveling salesman problem instance. So are there any questions about the reduction? So this is all the reduction will do, is it converts that instance into one of these. So it takes a Hamiltonian cycle instance and converts it into a traveling salesman problem instance. And since we're obviously studying the decision version, just keep this in mind that we're asking as a question. We're not trying to actually find the least weight Hamiltonian cycle. But the proof will come right out of it. Yes, exactly. Wherever there isn't an edge originally in that graph, I'm just going to add it in, and its weight is going to be 2. That's exactly it. Very good. So that's all. It's a really nice, simple construction, right? So I want to give you an intuition with this. So now I want to show you where the Hamiltonian cycle would be, happens to have a very close relationship with the one I have over there. And this is because of the way I constructed H. So very often the way these reductions work is they're very cleverly designed to force it to either say yes or no for the original problem. So here's the idea. I want to think of the edges with weight 1 as good edges that I want to use. The ones with the 2s, those are bad edges. I don't want to use those. Why? Because they're not in this graph. So you ought to think about these edges with weight 2 like they're penalties. They're like, oops, don't you go over there. Don't you go on that blue edge. Just stay over there. Just stay on the ones with the 1s. So naturally, if you look for our TSP tour with total length at most 5, well, look at it. Look. Okay, so let's see. I can follow along all of my low-cost edges, just like I did over there, right? So this is indeed a TSP tour, because it visits all the vertices distinctly, and at the same time, it visits them all, right? Right? I got them all. It's no different than that one, actually. It's just I didn't use the ones that are blue, and I omitted this edge. I didn't need that one in the original one. But here's the interesting thing. Because I visit each one of the vertices distinctly, this will actually be exactly equal to the number of vertices. Fascinating, right? So you might ask, okay, so why is that theorem true? So think about it. Suppose that there was not a Hamiltonian cycle here. So think about that. So there's a couple different ways you could prove this claim, but suppose that didn't have one over there. If to prove this claim, I would have to show you that there is not a TSP tour whose total cost is at most k, right? So notice that if I did have one right there, that means that there is no way I could visit all of these vertices in the simple cycle uniquely, right? That means I'm going to have to use an edge possibly more than once, right? Or you could almost imagine it just doesn't exist, right? But what is that like? Well, it's like if I were to revisit an edge, but that would increase the cost of my TSP tour by 1 more than n, right? Like I said, I think of these blue edges or any extra edges that I don't need as ones I want to avoid using. So the idea is that if I have these blue ones, if I use a blue one, you know right away, there is no Hamiltonian cycle right here because that edge simply doesn't exist right here, right? So there's a couple of ways you could formulate this argument. I'm going to leave the details for you in the proof, but the idea is very intuitive because in this construction, notice that the theorem says that it's at most n. Notice that this construction forces it that if it's a yes answer, it has to be exactly equal to n, and whenever it's a no answer, it has to be that the cost is greater than n. Does everybody see that? It's very subtle, but very interesting. So this is by the design of the reduction. So normally when these reductions are made, they're very cleverly designed so that you can prove a theorem that tells you the yes or no answer matches among both of them. So the whole idea is that if I had a nice algorithm that could compute TSP tours such that it was like this, I have a nice way of detecting these. Is that interesting? So are there any questions about the reduction that I did here? Any questions at all? So just a few things I want to touch upon. So just remember that when I built this graph, it's still polynomial in the size of the original graph. That's implicit in the polynomial-time reduction. The other thing is just remember, if this is a yes answer, it has to be that whatever I get out of here has to correspond to that. So if it's a yes answer here, it has to be a yes answer over there. If it's a no answer over there, it has to be a no answer here. Is that clear, everybody? So it has to have the same answer. In our case, it most literally is the same answer. Sometimes you can make reductions where one side has it where it's a yes answer, then the other side is a no answer, but you just complement and you get a yes answer. Normally this comes right out of the reductions claim for proofing it, the theorem. But the point is that there's a natural correspondence between the instances such that you can design an algorithm that gives you the yes or no answer if you had an efficient algorithm to solve this one. So, any questions at all about that? Give me 2 thumbs up if we're okay. So the thing I really want you to walk away from this course about reductions is that this is a very natural way to talk about many different kinds of problems. So as I gave you an example the other day and today, notice that now I've given you a direct way to talk about the Hamiltonian cycle problem as, in another way, as a subset of the instances of the traveling salesman problem. So it's almost like I'm talking about one problem, but I've transcribed it into the language of another problem. It's big brain. It's big brain. It's amazing. It's amazing. It's amazing insight because now you don't have to think about problems as these very confined things in their own buckets. Now what you could do is you could study one problem, phrase it in terms of another problem, but the polynomial time reduction gives you a means to transcribe your instances into the form of another problem so that, in effect, your problem is a special case of the other problem. So if you're interested in this one problem, if you find nice algorithms for your more general problem, then it gives you implications about the original one you're interested in. It's very fascinating stuff. But also the opposing side is that if you knew that the Hamiltonian cycle problem was difficult, that also, logically speaking, also means that the traveling salesman problem also is rather difficult to solve too. That's a consequence of the idea of the reduction, right? So that brings me to bring another core ingredient into this lecture. I gotta talk about some complexity classes. So I'm gonna talk about P and NP. So these are 2 complexity classes. So we've talked about the idea of having it where we categorize our algorithms by the efficiencies to solve those said problems, right? Or I have it where if one problem, I know I have problems that can be solved in linear time. I know I have problems that can be solved in quadratic time. We often like to classify or put them into buckets. So people that are interested especially in the consequences of complexity theory, what they would like to do is you can imagine all the problems we studied in this course. You can imagine you would have nice buckets you can place all of the problems we studied into them. So that when I come along and I want to study them, we have a classification for them. Just like what I said the other day, like if I'm studying animals, I want to know their relationships with each other. Likewise, if I was, say, playing Pokemon, I want to know which ones are the ghost types, which ones are the psychic types. It's helpful information so I know if I'm going into a Pokemon battle. I know that one was a little bit too much, but I'm going there today. I'm going there today. People will understand what I'm talking about some sort of the class. The animal analogy is good enough. So anyways, we're going to be focusing on problems that are solvable in polynomial time. You might ask, Dan, why ones that take polynomial time? Now, there's a very fascinating phenomenon that computer scientists started to observe in the mid-20th century, especially in the 1960s. Computer scientists such as Knuth and Jack Edmonds, especially Jack Edmonds, they started really making the clear observation that there are some problems that no matter how much theory they threw at them, there seemed to just be some barrier they were running into. But it seemed like there are ones that fall nicely into a category where they could solve them in polynomial time. Then there's these other ones. So if you're wondering a bit more about what I mean by this, I think one of the first papers that really gets into the heart of this, now this idea goes back a while. I think it was Jack Edmonds, if you're ever curious about this, Edmonds, it's from the early 60s. It's called Path, Trees, and Flowers. It's a very influential paper where he makes the connection between these two things. That there's things that can be solved in polynomial time, and then there seems to be things that are out there that need to be solved in exponential time. And we've actually run into this phenomenon before, actually, in this course. I just didn't put in those terms. For example, we talked about the fractional knapsack problem. We know how to efficiently solve that problem, but the 0-1 knapsack problem, every algorithm I've given you takes exponential time, right? So I want to give you a theoretical framework for now we can talk about this. So that's what the rest of this lecture is going to be about. So I'm going to hopefully layer this up nicely so that when we get to the very end, I can give you a very heavy implication that if you could do one small thing, you will make history. You'll make history. And I always like to inspire people. So anyways, so let us focus on problems solvable in polynomial time. So I'm going to first define the complexity class P. This one's very easy for me to describe to you. We've actually been studying a lot of problems that sit in P, just their decision counterparts. It is the class, or set, if you prefer to call it that, the set of all decision problems that are solvable. That means for every problem instance, it'll be able to tell me the answer. If it's a yes instance, it will tell me yes. If it's a no instance, it will tell me no. Are solvable in, and I'm going to put this clarification in here, but for us, we've never had to make this delineation. I'm not going to be going into too much detail about the delineation, but I'll give you some intuition behind it. In deterministic polynomial time. That means that the running time has to be big O. So note I am using big O here. It's big O of n to the k time, where I'll say, instead of saying where, let's go. Big O of n to the k time for some constant, k greater or equal to 0. So you actually know a lot of problems actually that sit in P. We just haven't talked about them in terms of that. For example, so if I have my complexity class P, it consists of all sorts of different problems that we've actually been studying before. So for example, you know how actually it was on Tuesday, I told you how I could talk about the minimum spanning tree, for example, as a decision problem. We know how to actually answer questions such as those that I had for the decision version of the minimum spanning tree problem. Can somebody tell me what's an algorithm I could use to solve the decision version of the minimum spanning tree problem? We studied it in this course. Which one? So I'll give you a tip while you're giving me your answer. What you do is you just simply use that algorithm, and then you would just check with an if statement. You'd say, if whatever the value you get from this algorithm is at most k, then you'd say yes, otherwise you'd say no. So what's the algorithm you would have just before this? So think of the blob. There's one algorithm that we had, well, actually there's technically two, but there's one specifically for the minimum spanning tree problem that we had the blob. And the blob went around devouring the graph, but this blob was it was just wanted to go wherever it was kind of closest to the blob itself, not from where it starts. It starts with a P. It's Prim's algorithm. So we know that problems like that, so for example, minimum spanning tree, the decision version of that, or decision variant of it is in P. We have several or many problems that can be classified in P. For example, the search problem. One of the first problems we looked at in this course. The search problem, that's also in P, right? You could use linear search. There's lots of problems that are in P. So this covers actually a lot of problems we've actually studied in this course. For example, I could recast, for example, the fractional knapsack problem as a decision problem too. So I could have fractional knapsack decision variant too. I'll just put DEC after any what I'm talking about is decision variant, because we've talked about optimization problems a lot as well. But the point is that many, if not almost, I would say a very large portion of the problems we study in this course, they have a decision version of them that sits in this complexity class. So you might be asking, Dan, where are we going with this? Well, this seems to, what my point is that wherever we had efficient algorithms, they're in P. Does everybody see that? So like all of the ones that we had really nice running times for our algorithms, they all set in P. So what I want to do, so it seems like a good way of thinking about efficiency when we start thinking about problems that are actually much harder, such as the 0-1 knapsack problem, or say the traveling salesman problem. Those problems, they seem a little bit more escapable from us at this current time. We certainly lack the theory to really study them in the same well, it's a lot of work on these types of problems, but most certainly it is still up for debate whether there exists efficient algorithms for them. However, we have lots of evidence saying that they don't exist, but we don't know with absolute certainty, like we've made a lot of the claims in this course. So that brings me to talking about another notion of computing to you. So I will tell you up front, this is going to be at first a little bit abstract, because we're so used to us having algorithms that follow the exact intuition that we're familiar with for a computer program. So I'm going to cast it in terms of another concept that is used for programming, but I will tell you briefly that it actually has a connection with a much more abstract notion of computation. So next I want to study, so we know what P is. Seems pretty straightforward, right? I'm going to talk about this thing called NP, but before that, I got to give you some intuition behind it. My apologies. Let's instead of study, let's discuss it. We discuss verifying or checking a solution. So for many of the problems we studied, right, we have it where we have a problem instance, and then we have an algorithm that's given that problem instance, and then it produces a solution, right, when the algorithm is correct. Now, suppose that I gave you a problem, and now instead of it being where I give it just straight up to an algorithm, suppose instead that along with the problem instance, somebody gives you some proof, a certificate. And the certificate is very short for me to check it. Now, suppose that I had an algorithm that I could use to check this proof if it exists. And if it's a yes, if this is trying to tell me, hey, look, this is a yes answer for this yes instance, the algorithm will be able to test the proof to tell me if the original instance has to be indeed a yes instance. Let me talk a little bit more about that, because at first it sounds really abstract and strange, right? We've never talked about anything remotely sounding like that, right? That's really weird. So let me characterize this a little bit more carefully, and I'm hoping I can bring this down to a level that we can understand. Suppose if somebody gave you a problem instance, X, and some proof, which sometimes this is called a certificate. Called a certificate. Why? So the Y is the name of the proof or certificate. and claimed that y shows x is a yes instance. So imagine somebody gives you this proof. And your job, so what we're going to think about is, imagine somebody gives you this proof along with the problem instance, and they give you this proof. Your job is to check their proof, and keep in mind, you can think of the y almost like it's helping you solve the problem even. But the idea that we want to have in our minds is that somebody gives you this proof, your job is to check or verify that their proof indeed tells you that the problem instance is a yes instance. So it's almost like you want to verify. So somebody gives you an answer, you want to verify if y is indeed telling you that x is a yes instance. So I must stress that there is a symmetry, it's not symmetric, so I must stress that in the setup of this, y has no responsibility to tell you it's a no instance. It just has to tell you if it's presuming it's a yes instance, that I have to have some way of doing that. Now you might ask, okay, so what if this proof is really long? Well, that's too bad. That's too bad. There are a lot of ways we can cast that, but we're going to be interested in when y, the certificate, is short. So it makes it easier to check. So, assuming the description y is polynomial in the length of the input x, which we've denoted before at the beginning of this course, denoted as the bars with x is short. Can you, in polynomial time, test whether or not y gives a yes answer for x? So just to be clear, we're confirming that x is a yes answer. So this is the notion of a verifier. So this is the notion of a verifier. So this is what a verifier is. So I'll give you the plain language description, and then we'll do a couple of examples to see what a proof is, so we can understand what it means for there to be a proof. Is that, because the thing in our definition, as we're going to see, is that the proof, all that has to happen is the proof has to exist. So we have to have a lot of choice of what this proof will look like. But let me just finish this one sentence here. In plain language, for any yes instance, there will be a short, easy to check proof that its answer is yes. So just to be very clear, so notice that there's this part about checking. That's going to be one of our algorithms, so that we get to design this. So we're going to be designing an algorithm that performs this check on the proof. So it has to exist, this proof, So we have control over finding out what this proof will be. The intuition for this will be that the proof will look like a solution. So I want to give you some intuition behind how you would figure out what the certificate would be for a problem. Because you can have several different choices for it. It's just that we want to make sure that our proofs are polynomial in the length of the original input size. So let's talk a little bit about this. But the big thing is we only care about the proof here. So if we pick the proof or certificate appropriately, what we need to do is just check, or what we call verify it. Now to be very clear, we're not responsible for determining if a no instance outputs no. We're not responsible for that. We're just checking the proof. Just to be very clear. So we do not have that responsibility here. You might ask, Dan, why would that be the case? Because this notion of verification is going to be corresponding to another concept called non-deterministic or non-determinism in terms of algorithms. Which, in that context, computation gets a little bit more clairvoyant, and the ability to make guesses all of a sudden becomes way more efficient to do. So I want to do some examples just to give you a flavor for what this is about. So naturally, what is a proof in this context? Or certificate? So I must stress that for most problems, it will be a solution. I'm going to put that in air quotes. It will be a solution to a yes instance. Yes instance in appearance. So let's just do a quick few examples. So if I give you the minimum spanning tree decision variant. So for the minimum spanning tree problem, if I wanted to demonstrate, so somebody gives you one of these proofs, and I want to check and know if there exists a spanning tree whose total cost is at most k. What would be a nice natural thing for me to give you so that you can verify that I'm indeed telling you that, yeah, this is a spanning tree of the total cost of most k? So let's just say the most obvious thing. What would be the most obvious thing for someone to present to you so you can check it against the input instance? Think of the most obvious thing. Don't make it more complicated than it has to be. I'll tell you, it's quite similar to what I just said. So suppose that I want to say X. So remember, I have an input instance X, and I have a certificate. I want to be able to have it so that I can give you the certificate, and if it is indeed that X is a yes instance, my certificate should be good enough for me to determine that, but yeah, X is a yes instance. But it has to also be short. But it doesn't have to be like wicked short, just as long as it's polynomial the size of the input. So based on my intuition that I was giving you here, well, I just said it to you, right? You can just give me a spanning tree. So naturally, if you want to verify that this indeed is a yes instance, all you have to do, your job will be to just check. So you would check that it is a spanning tree. A spanning tree that contains all the vertices in G, and then check its total cost or weight is at most k. right? That's how I can verify if I gave you a spanning tree, or what would be presumed to be a spanning tree, how I could verify, so I can tell you if, yes, this is in fact a proof that verifies that X is a yes instance, or I can reject the proof and tell you, no, you just gave me a bunch of bull. But the thing is the proof is what matters here. We're not trying to say that X is a no instance. I want to know if the proof is valid, as in it's telling me, yes, it's a yes instance, or no, this proof is a bunch of baloney. So you might ask, Dad, where does this intuition of the proof come from? So think of it, if it really helps with the intuition of this, think of it instead of like our problem we had earlier, like the Hamiltonian cycle problem. So you know how when we had the Hamiltonian cycle problem, if you tried to design an algorithm that actually solved that problem, you probably can think of a very natural way to do this with backtracking. So you might just try all possibilities, or just do a brute force search. You just permute all possible orderings of the vertices, and you take which one leads you to a Hamiltonian cycle, or you've checked them all and you say, no, it doesn't exist. This naturally takes exponential time, right? So what if, so this is the big brain, I know I'm totally borrowing this idea. Here's the idea that I want you to kind of walk away from this from. Because this idea of verification naturally corresponds to the idea of non-determinism. Now, in non-determinism, which is something that you'll see if you take the class CS411, in non-determinism, the idea is that we have the ability to make perfect guesses. So I can design an algorithm that has several branching pathways, almost like a backtracking algorithm. You know how in the backtracking algorithms you can have like a big search tree, say our state space tree. And you would naturally have it where you do a depth first search through the tree, right? Well, in non-determinism, if you design a so-called non-deterministic algorithm, what this will be capable of doing is it can branch on all possibilities simultaneously, and at the same time, it knows which way will lead you to a yes answer. Which sounds absolutely like magic, right? Like, we don't have a computer that's capable of that. Because it actually relies on clairvoyance, the ability to know the future. If you think of it a little bit more carefully. So a natural way you could think about this idea of having a short, concise proof, it corresponds naturally to if you had a large search space tree, where the space tree's depth, the search tree, its depth is bounded by a polynomial in the height. So it means that if you had it where you could go through one of these branches and you had some magical way to know which path of execution leads you to the yes answer, if it exists, this corresponds actually naturally to this idea of the proof. It actually tells you what decisions you need to make if it was a yes answer, or it will tell you how to reject a path of execution in such a system. So if you want to learn more about that, take CS411. It's very natural. But I'll give you the simpler way of me to explain it to you. And I always like explaining it like this to students. Okay. So I'm sure, if not, you've never seen it before, or may have seen it before, or even heard about it. Very often in media, we would very often, or even just think of or imagine our best pals in the world, our pets, right? Like our cats or dogs. Sometimes you would have like say you have a favorite dog. There used to be shows like Lassie, for example, or The Littlest Hobo. I especially like The Littlest Hobo. That's the man. It always brings me to tears, man. It's one of those things that if you're from the 80s like me, it's a very highly nostalgic. The point is, it's in these shows, these dogs almost had like super abilities to know what they needed to do to resolve an issue, whether it be, oh, little Billy went missing, or Timmy went missing, or, oh, the robber took my favorite thing from me. So what these dogs would do in the show is they would help the people find out what happened. And then they would go off to do their thing, or they would be with their family. Like Lassie would be with their family. Littlest Hobo would go on and go on another journey somewhere else. But here's the idea. So if I gave you a Hamiltonian cycle instance with no information at all, you'd agree with me that most of the techniques we have would rely on take exponential time, right? Well, what if I had the littlest hobo to help me? Well, what if littlest hobo could tell me where the missing gold is? So, littlest hobo, how would littlest hobo do this for me? How would the dog do that for me? Well, the littlest hobo could actually just present me the sequence or where I need to go to find the gold, right? But what if finding the gold is actually the same as finding the Hamiltonian cycle? What if it's behind me? My apologies. Rest in peace, headphone users. Actually, hopefully it wasn't that bad. But the point is that the verification process, I'm pushing it onto the littlest hobo's proof, which in this case, the littlest hobo is helping me find the gold. I don't have to find the gold myself. I just have to check if the littlest hobo is making stuff up or not, which happenstance. The great thing about non-determinism is if there is a way to find the answer, non-determinism will guarantee me they'll find it through some path of execution that will be, if it can be done in polynomial time non-deterministically, this actually corresponds to a proof that is actually of polynomial length in the input size, which is very fascinating. But that being said, I'm going to give you, let's do one more example quickly, just so you get an idea for what I mean by this proof. I just always like to explain this so that you understand that we're not trying to solve X. We're not trying to solve it. We're trying to verify Y given X. So I want to know if X is a yes instance if Y indeed tells me that X is a yes instance. I'm not doing this cold turkey at all. But just do know that this notion of verification naturally corresponds to having an agent that has pure clairvoyance, just like the littlest hobo, or Lassie. Lassie is just totally OP, man. I've seen some of those old episodes from the 50s, man. Lassie just tears into people. But here's the point. Let's talk about another proof. So, for example, somebody could give you a cycle. Naturally, if you give me a cycle for the Hamiltonian cycle problem, you would check it contains all the vertices of G, and that it repeats no vertex twice by following the edges. Just like our example we have with the littlest hobo. So imagine the littlest hobo gave you this. And the littlest hobo knows how to get the S answer if it exists. So all I have to do is I need to come up with a way to check the proof. By following the edges of the cycle. So I have a question for you based on these two examples here. Does this seem intuitively much simpler to do than me having to just find the answer myself, cold turkey, without the help of the littlest hobo? Like doing this. Do both of these seem rather things I could solve efficiently? So just verifying them. So if somebody gives you a spanning tree, and all you have to do, presuming that spanning tree is in fact one that gives you a yes answer, could you tell me that will be an answer or proof that verifies that X is a yes instance? So these are actually just me, believe it or not, what I've just described here are actually just very high level descriptions of algorithms to you. Does everybody see that? These are actually just descriptions of algorithms. So what I'm telling you is that this actually corresponds to a notion called a polynomial-time verification algorithm. So I'll just say above the stuff in parentheses actually are polynomial-time verification algorithms. So they'll be able to get, so if I give you the proof, I give you an instance. If y is in fact observing or witnessing a yes answer, if your algorithm can check this, given this proof, remember, you get choice over this. I don't have to pick this as the proof. I can make a different one if I want. This is just a very natural one for me to pick. Just the point is that the proof has to be polynomial in length. It just has to exist. It doesn't have to be for any arbitrary proof. You get to have choice over it. So the point is it has to run in polynomial time. If it runs in polynomial time, which you can make clearly both of these you can do in polynomial time given a spanning tree or given a cycle, right? You can do both of those in polynomial time. These are what we call polynomial time verification algorithms. So naturally, you would like to know what that means for us. So that's how I'm going to define NP to you. So suppose the littlest hobo gives you a proof. Remember, littlest hobo knows how to do this so that the proof is only a polynomial in length. And you have a way in polynomial time to check the proof, or what we call verify the proof. So if it is a yes proof, as it observes that there's a yes answer, and that means that it shows you that X is a yes instance, then we say that, yeah, look, there's a polynomial time verifier, but any problem that has one of these is actually going to belong to a complexity class. So complexity class NP. So a decision problem, pi, is in NP if there is a polynomial time verifier for it. I must stress, if you're looking for the formal definition of the polynomial time verifier, I have it actually in the notes, but for the purposes of time, I've just omitted it. I just said it verbally for you. If there's a polynomial time verifier for it. Which the polynomial time verifier is the polynomial time verification algorithm. For it. Another way you could equivalently define this is NP is the class of decision problems. Decision problems that can be solved in non-deterministic polynomial time. So if you're wondering what NP stands for, it stands for non-deterministic polynomial. It doesn't see, it's not polynomial, it's non-deterministic polynomial. As I told you, this notion of non-determinism is something, if you're curious more about this, see 411. You talk all about this and all of its lovely juiciness. The notion that you can have a computational model that has this so-called clairvoyant-like property where it has the ability to always perform perfect guesses, to perform a path of execution through, say, for example, a brute force search. It's able to execute them all effectively in parallel, but it knows which way gets you to the yes answer if it exists. Which is very strange. It's a very strange idea. It's like magic. And I'm not even kidding when I say that. So one thing I want to mention to you is we talked actually about the traveling salesman problem. We talked about its decision variant, right? I have a question for you. Is TSP DEC in NP? I'll give you a tip. It's very similar to one of our examples we had over there. So I'll tell you that DSP deck is an NP. And the proof I'll just leave in the notes. So if you want to see the proof for this, it's very short. It's very similar to what I have actually here on the left board. Just the difference now is instead I have to just sum up all the edge weights. It's like the Hamiltonian cycle problem I have over here, right? I just have to make sure I add up the edge weights and make sure that matches at most. It doesn't exceed K, right? In fact, that's actually how the algorithm you'd present works. So in the proof for this, what you do is you present the polynomial time verification algorithm, which all you do is you give me what the certificate looks like. Can somebody tell me what the certificate would look like? Can somebody tell me? What would be the certificate here? So there's several ways you could give me a certificate for this proof. So think carefully about what we did earlier. So there's a lot of valid answers actually for this one. So I'll let you think about it. I'll give you one example of one. You could just simply give me, so you could just simply use a tour or cycle, and that's good enough. And then you just simply test this. So the proof, so the algorithm, the verification algorithm, so this is what your verification algorithm will do. So it just performs the test. It just tests the certificate. It'll tell you yes or no for the proof. So if it's yes, that means that X is a yes instance. If it says no, that just means that the proof is just a bunch of bull. It doesn't necessarily mean that it's a no instance. So one thing I want to point out about this is that TSP-DEC, as I said earlier, the best known algorithms for solving this problem take exponential time. I'll say exact algorithms. Take exponential time. In fact, there is a well-known dynamic programming algorithm for this. You can use dynamic programming to solve this. I believe, if my memory serves me correctly, it's called HeldCarp. If you want to go find it, it's called HeldCarp. If I had another month for this course, I would teach it to you. But yeah, so notice that if I think about this definition of NP, there's something I naturally want to think about. Is P and NP related to each other? So let's talk about this. So we have enough time for me to lay out a couple of important concepts, and I'm hoping if you give me a couple of minutes, I can give you some concrete examples of why you might want to care about the connection between these two complexity classes. So a natural question. So the first question I have for you is P a subset of NP? So that's the first question I have for you. So remember, these are two sets. So it might be that every decision problem in P is also actually a decision problem that's in NP. So I'll tell you that the answer to this one is actually yes. And actually the proof goes something like what I'm just about to show you here. Okay, you know how I had it where I had the littlest hobo. The littlest hobo gives me a proof, right? And I check the littlest hobo's proof. Littlest hobo goes, "Woof, woof, woof, woof," and I follow the littlest hobo, right? And littlest hobo, I can check the answer. Wow, what can I say about these problems, the ones in P? Do I need the littlest hobo's help to verify anything in polynomial time? Yes or no? Any ideas? Any ideas? Do I need the littlest hobo? If I'm considering a problem that's in P, do I need the littlest hobo's help to solve the problem? Say if I want to verify an instance is a yes instance. Do I need the littlest hobo's proof? If I want to verify that X, if it's a yes instance, it tells me the answer is yes. Do I need the littlest hobo to help me to do that in polynomial time? Or can I just tell the littlest hobo, go for a nap, you can relax for once, you don't have to be super dog every day? Well, believe it or not, you can actually get away with just not even needing the help of the littlest hobo here. Because if you're in P, that means you have a deterministic polynomial time algorithm, right? So you can just run the polynomial time algorithm, right? You don't need the proof at all. In fact, the proof works just like this, is that you just assume I'm given some placeholder proof, and then I just run the polynomial time algorithm for that decision problem, and if it's a yes answer, just say yes. I don't need help. I don't need help from the littlest hobo. So that's why this is true. Now the natural question is, is NP a subset of P? This we don't know. If you talk to a lot of different computer scientists, many of them will tell you that the answer is no, but we don't actually have a proof for this. This is an open problem. This is actually, we still don't know this. This has really been studied heavily since the 70s, and people still don't know. So this is actually the P versus NP problem. And it just simply is P equal to NP. So you might ask, okay, so why would you care about this problem? Well, I want to introduce you quickly to two important definitions and one last bit, if you give me 2 minutes. So it's the notion of NP-completeness. So there are hardest problems. So there's this notion of having a hardest problem in NP. So I'm going to first define what is called NP hard. So a problem pi. So note that this can be an optimization problem. Very often if you have an NP-complete decision problem, the optimization version is NP hard. Is NP hard if for every pi prime in NP, pi prime polynomially reduces to pi. So that means that you can take any one of the problems in NP, there exists a polynomial time reduction that takes this pi prime and converts it to instances of pi. So that means that you can take every one of the instances of problems in NP. So that means like every one of the problems that's in NP. I can take the instances of those, I can convert them over to my problem. So what does that mean? All of those problems are at least as hard as my problem, right? So you might ask, which ones are the hardest ones in NP? Those are what we call the NP-complete problems. So remember, because it's NP complete here, must stress that the hard means at least. It doesn't mean that it has to actually be in the set that is mentioned here. It's at least as hard as the hardest ones. So the NP-complete problems, these are decision problems. This is a decision problem pi. We say pi is NP-complete if 1, pi is in NP, and 2, pi is NP hard. So, for example, we talked about actually a couple NP-complete problems today. We actually talked about some NP hard problems throughout this course. So, for example, a 0-1 knapsack problem. This is actually an NP hard problem. Traveling salesman problem, its decision version is NP complete. Its optimization version is NP hard. And here's the thing. this gives you the groundwork to say that there is actually a whole set of problems that fall into this. And you might ask, when did we ever discover these things? Like how do we know that these problems even exist? One of the first things we ran into in the 1970s in computer science was the existence of this. Because it's very easy to come up with a definition, like the mayonnaise, coming up with a good sandwich. It's very easy to come up with a definition, but does it actually exist? That is the real question. And the early 70s, this answer was actually addressed by, for example, Stephen Cook. So I want to mention just a couple of quick things. So one, for example, is the Cook-Levin theorem. So the Cook-Levin theorem. There's a problem called Boolean satisfiability, or the satisfiability problem. This is where I give you an arbitrary Boolean expression which has Boolean variables that either are set to true or false, and they can have combinations of ands, ors, or nots, and they can be parenthesized. And the question is, if I give you one of these formulas, does it have an assignment of its variables such that it evaluates the true? The question is, what exactly, that sounds like a really broad class of problems, right? Well, that was actually the first NP-complete problem ever discovered. It was discovered in the early 70s. And this is called SAT. So SAT is NP-complete. Now, I must stress that because of the theory of reductions, I have to also mention that problems that are NP-hard or NP-complete seem intractable. We don't presently have polynomial-time algorithms for any problems that are NP-complete nor NP-hard. We don't know how to come up with polynomial-time algorithms for these. And you might ask, what kind of machinery can we use from our last couple of lectures to discover more NP-complete problems? And in fact, you could use this machinery that I've given you the last couple lectures actually to establish problems are NP-complete or NP-hard. So here's an alternate definition for NP-complete. So you don't have to consider every problem an NP. Once you have an NP-complete problem, remember what I said about a reduction. So if pi is NP-complete, and pi prime is an NP, and there exists a polynomial-time reduction that takes instances of pi, reduces them to pi prime, then pi prime is also NP-complete. This is because of the idea of the polynomial-time reduction. I've only converted the complexity of the problem by a polynomial degree. That's it. So I must stress that many of these problems do exist, and I'm going to stop here. I just want to mention that many problems that affect many domains. So I'm talking about everything from packing to scheduling to computational geometry. All actually have problems that are these NP-complete ones. You will run into them if you're interested in very fascinating problems. Affect many domains. And here's the big point. And I will stress that if you want some examples of these, including ones we've talked about in this course, I want you to look at the notes after class because we've run out of time here. I want to give you one last theorem so that we leave on a powerful note. I want to give you my last theorem for this course. Last theorem, it's just one sentence. Is if some NP-complete problem is in P, then P is equal to NP. That means even if you can find for any one of these NP-complete problems, so whether it be the decision version of the traveling salesman problem, whether it be SAT, whether it be Hamiltonian cycle problem, if you can find even for one of these problems a polynomial-time algorithm, that means that that NP-complete problem is in P, and the entire complexity hierarchy between P and NP collapses into a single class, and that would imply for many, many NP-complete problems that they all have efficient algorithms. And you might ask, what's the implications of this? It's very wide, very deep. So, that being said, there's a lot of ways computer scientists have been trying to resolve issues around intractability. Some study this more from a theoretical standpoint. Some people buff up the model of computation. For example, they consider things like parallel computing or quantum algorithms and things like that. But that doesn't get away from the intractability and the nature of this problem. It just obfuscates it to the model. But the big point is that I want you just to be aware that there's these earth-shattering results, but they're all intricately tied around the idea of NP-completeness. So, that being said, I want to say thank you very much for your time. It was a pleasure to be your professor this term. It's always an honor. It always humbles me to hear these things from my students, and I've had a great time this term. I want to say thank you very much, and have yourself a beautiful day.